Good day, everyone. We are Group 3, and today we're going to discuss about the crystalline solids. So here are the objectives. At the end of the unit, the student should be able to define crystalline solids, enumerate the characteristic of crystalline solids, give the types of crystalline solids and their examples, describe the arrangement of atoms in the common cubic crystal lattices, simple, body-centered, face-centered, hexagonal close packing, and cubic close packing. Calculate the packing efficiency for each lattice, and solve problems involving crystalline solids.
Crystalline solid. Solid can be classified based on the arrangement of particles. They can be either crystalline or amorphous solid. If the particles are arranged and organized in a specific location or form rigid in long range order, the solid are crystalline. Crystalline solid have symmetrical structure and thus when cut, flat, and smooth surface can be seen. For example of crystalline solid is salt. So yung crystalline solid, basically, ito yung mga solid materials kung saan yung mga atoms and molecules ay nakaayos at may paulit-ulit na pattern na sa isang substance. And yung pattern na yon, it is tinatawag siyang crystal lattice. Kung saan, ito yung magbibigay ng shape and properties sa isang solid. For example, is yung asin. Pansin nyo, yung ibang shape ng asin is pa-cube. Pa-cube siya. That is because of atom and salt are arranged in cubic lattice. So kapag gumawa ng asin, yung molecules ng asin, nagpo-form siya into cubes.
Ionic crystal. Ionic crystal are a type of crystal composed of ions held together by electrostatic attraction. Typically, they have high melting point and do not conduct electricity in their solid state, but they can conduct when melted or dissolving in water. An example of ionic crystal is sodium chloride. Covalent crystal. Covalent crystal are made of atoms that are bonded together through covalent bonds. These crystals are hard and also have high melting point, but they do not conduct electricity in any state. Example of covalent crystal include diamond and quartz.
Metallic crystals. In a metallic crystals, the principal constituent particles are atoms of the same metal. Usually, metals have 1 to 4 outer electrons, so they are empty or betals in the last energy level. So, metallic crystal is yan. Particles are metal atoms arranged in a regular or repeating pattern, which form a structure known as lattice. The most significant characteristic of metallic crystals is the nature of bonding between metal atoms, which is quite different from that is molecular or ionic crystal. Let's dive deeper into features of metallic crystals, their bonding and properties that arise from them. Yan. Una, structure of metallic crystal is lattice arrangement, face-centered cubic, FCC. Yan. Hexagonal close pack, HCP. Yan. Body-centered cubic, BCC. Yan. Yan yung sa structure of metallic crystal. And sa electron configuration and bonding are metallic bonding, free electrons, empty or betals. Yan. Sa pangatlo, properties of metallic crystal is electrical conductivity, thermal conductivity, malleability, and ductility. Yan. Laster, high melting and boiling points. Strength. Yan. Yung pang-apat, alloys and their properties. Yan. Yan yung mga alloys. Yung mga steel, ganyan. Iron and carbon, yan yun. Copper and tin. Yung pang-lima, key features of metallic crystals are strength and durability. Yan. Flexibility, wide range of application. Yan. There are example of metallic crystal. Sodium, copper, gold, iron. Yan. Sa sodium is metal forms as a simple metallic structure with BBC. Yan. Body-centered cubic. Yan. Arranged in is a good conductor of electricity and heat. Sa copper has a PCC, base-centered cubic, arranged in and is a widely used in electrical wiring due to its high electrical conductivity. Gold is example of metal with a very high degree of malleability and ductility. It has a PCC structure and it's prized for its aesthetic properties such as its luster. And sa iron naman is BCC structure, body-centered cubic structure at lower temperatures, and a FCC structure at higher temperature. It alloys has steel. Meron siyang steel and for constructions, tools, and machinery due to their strength. Yan. In conclusion of crystals, metallic crystals, the metal atoms are bonded through the metallic bonding where the valence electrons are decollized in C and move freely within the lattice. This unique electron arranged in responsible for key metals properties such as electrical and thermal conductivity, yan, malleability, ductility, and luster. Understanding the metallic crystal is fundamental to understanding the behavior of metals in everyday life. From materials are used in construction to technology used in electronics. Molecular crystals are molecules held by dipole-dipole between polar molecules. Dipole induce dipole between polar and nonpolar substance. Dispersion all substances and hydrogen bonding in substance containing hydrogen attached to oxygen, nitrogen, and fluorine. So, molecular crystal are the type of crystalline material where the individual molecules are held together by intermolecular forces rather than by covalent and ionic bonds. These forces influence the physical properties of crystals, such as its melting point, hardness, and solubility. Let's discuss the different intermolecular forces that can hold molecular crystals together. Yan. Yung number 1, yung dipole-dipole interaction between polar molecules. In molecular crystal, where all the molecules are polar, dipole-dipole interaction occur. A polar molecule has a partial positive charge on one side and partial negative charge on other. The positive end of one molecule is attracted to the negative end of another molecule. Yan, yung example niyan, a good example niyan is interaction is in crystal of hydrogen chloride, where the positive hydrogen end of one hydrogen chloride molecule is attracted to the negative chlorine and of another hydrogen chloride molecule. Yan. Yan. Naging effect of ng crystal properties is dipole-dipole interaction generally result in moderate melting points as this interaction are weaker than covalent or ionic bonds but is still significant. Ayan. Pangalawa, dipole-dipole induce dipole interactions between polar and nonpolar substance. Ayan. A polar molecule can induce a temporary dipole in a nonpolar molecule. The electric field of the polar molecule causes the electrons in the nonpolar molecule to shift, creating a temporary dipole. This temporary dipole is then attracted to the polar molecule. Yan. Example of this interaction when a polar molecule like hydrogen chloride interacts with a nonpolar molecule like argon. The polar hydrogen chloride induce a dipole in the argon atoms, and the two are attracted. Yung naging effect niyan ng crystal properties, this interaction tends to be weaker than pure dipole-dipole forces, but still plays in a role in determining the structure and properties of molecular crystal, where nonpolar and polar molecules interact. Pangatlo, dispersion forces, London dispersion forces present in all substance. Yan. Dispersion forces are the weakest intermolecular forces, occurring in all molecules non-polar and polar. They arise due to the instantaneous and fluctuations in electron density that create temporary dipoles in molecules. These temporary dipoles induce corresponding dipoles in neighboring molecules, resulting in attractive force. Yan. Example niyan is nonpolar molecules like nitrogen experience London dispersion even though the nitrogen molecules don't have a permanent dipole. The movement of electrons creates transient dipoles that lead to weak attraction between the molecules. Yan. Effect of crystal properties, dispersion forces contribute significantly to the behavior of non-polar molecular crystals. In generally, the larger the molecule or atom, the stronger the dispersion forces, leading to higher boiling and melting points. Yan. Hydrogen bonding in molecules containing hydrogen bonded to nitrogen, oxygen, or fluorine are hydrogen bonding, especially and relative strong from dipole-dipole interaction. It occurs when hydrogen atom is bonded to a high electromagnetic atom such as oxygen, nitrogen, and fluorine. The electronegative atoms pulse electron density away from the hydrogen can interact strong with a lone pair of electrons or another electronegative atom, oxygen, nitrogen, or fluorine, from neighboring molecule. Yan. Example niyan, water is a classic example of substance with hydrogen bonding. The hydrogen atoms in one water molecule are attracted to the oxygen atom in another molecule. This interaction explains why water has a high boiling melting points compared to another molecules of similar size. Naging effect niyan crystals properties is molecules that form of hydrogen bond typically have higher melting and boiling points because hydrogen bonds are significantly stronger than dipole-dipole and dispersion forces. The crystal structure tend to be more organized and the substance may be exhibit a strong cohesion. In conclusion of molecular crystal, the interaction forces, dipole-dipole, induced dipole dispersion, and hydrogen bonding dictate the overall physical properties of crystals. Understanding this interaction helps explain the diversity in the behavior of molecular solids from the lower melting points of noble gas crystals to the higher melting points of substance like water.
Packing efficiency is a crucial concept across various scientific disciplines and practical applications, encompassing the optimal arrangement of objects within a defined space. It, it quantifies the proportion of the same space occupied by the objects themselves, con- contrasting it with the volume of empty space or voids. The higher packing efficiency, the more densely the objects are arranged, leading to implications for material properties, manufacturing processes, and even biological systems.
A basic concept in crystal structure is the unit cell. It is the smallest unit for volume that permits identical cells to be stacked together to fill all space. Furthermore, there is only one lattice point at each corner of the cube-shaped unit cell. A BCC unit cell has atom at each corner of cube and atom at the center of the structure. According to this structure, the atom of the body's center is wholly belongs to the unit cell in which is present.
A center cubic cell, FCC or cubic close packing, CCP. This structure contains atoms each with coordination number of 12 6 in this own layer, 3 in the layer above and the 3 in the layer below. FCC can be formed by forming a hexagon layer like a 6 in the same layer, 3 in the layer above and below, like forming a repeating hexagon pattern that makes material like gold, silver, and aluminum very dense and stable, and in which each atom touching other atoms. The atom in the second layer are then placed above the triangular depression in the first layer, and the atoms in the third layer are positioned above the depression in the first layer that was not utilized to form the second layer, the fourth hexagonal layer structure. Hexagon close packing, HCP. This is similar to FCC except that the third layer is directly over first layer split to form an AB. Repeating structure, the coordination same as PCC. Same as PCC, each atom touches 12 other atoms, 6 in the same layer, 3 above the 3 above and 3 below, but creating very dense and strong arrangement commonly found in metals like titanium and magnesium. X-ray diffraction. All we know about crystal structure has been learned from X-ray diffraction studies. X-ray diffraction refers to the scattering of X-ray by the unit of a crystal solid. So, X-ray diffraction is a scientific technique used to understand the arrangement of particles inside the crystal like solid materials. It studies how X-ray, a type of high energy light, reacts when they hit the atoms in a crystal. So, 1912, a German physicist named Max von Laue suggested that because the wavelength of X-ray is almost same the distance between atoms in a crystal. So, sabi niya dito, because the wavelength of comparable in a magnitude to distance between lattice point and a crystal, the lattice should be able to diffract X-ray. So, they can scatter or spread out. When they scatter, patterns are formed that can be observed, and this pattern give clues about how the atoms are arranged inside the crystal.
Here's our conclusion. Crystalline solids are a fascinating and important class of materials with a wide range of applications. Their ordered structures give them unique properties that make them valuable in many fields. From electronics to medicine to construction, understanding the structure and properties of crystalline solids is essential for developing new materials and technologies.